Hello everyone, in this video we're going to look at the chapter 8, 8.1 to 8.4, the lesson 7's course content. And the 8.1 is introduce random sampling. And first we want to look at the definition of population. So what is population? Population is, look at the totality of observation in which we are concerned, whether the time, whether the number be finite or infinite, constitutes what we call a population. Population means all. Okay, so it's totality of observations, so all of the observations. Okay. There was a time when the word population referred to observations obtained from statistics study about people. Well, now we use the population to means they consists of totality of the observations, all of the observations in which we are concerned. Okay, and you can read this page 226 about example of population. And next we'll introduce a definition, which is a sample. What is a sample? A sample is a subset of a population. For example, okay, if this is the population, the set, then sample is just a subset of a sample, and the whole thing is population. So a sample is a subset of a population. For example, all the students in UWC could be a population. Okay, we want to do the research on all the students studying at UWC. But now UWC online is just a sample of the students studying at UWC. So it's a subset of our population. Okay, we normally want to study on the properties of the sample, and then use that to estimate the population parameter. Okay, so and there's one very important thing is, if you use a sampling data to produce some interference. For example, you got a sample mean value and use that mean to represent the population mean. Obviously there exists some error. Okay, so that's what we call, you can say, any sampling procedure, that procedural interference that consistently overestimate or constantly underestimate some characteristic population is said to be biased estimation. To eliminate any possibility of a bias in the sampling procedure, is desirable to choose a random sample. So normally we want to randomly choose a sample, and then it will not have any, it actually decrease. You will not say, oh, they are 100% accurate. It would still have some error if you use that to represent the whole population. Okay, so we do random sampling. It's much better to just choose a group of people to represent the whole population. Okay, so random sampling is, random. Okay, the word random, that it's just a selected one, another one. It does not have any rules, so it's all randomly. Definition 3 is let f, x1, x2, xn be any independent random variables. The key word here is independent. Okay, if they are independent, then each having the same probability distribution, fx define x1, x2, xn to be random sample of size n from population fx, and right is a joint probability distribution as. So the joint probability distribution is fx1, x2, xn. This is a joint probability density function, equals fx1 times fx2 times fx3 times continue fxn. Okay, this equation, this probability joint probability distribution, this one to be true, it has to be all the variables are independent with each other. So then you can multiply all the distribution, and together it's going to be the joint distribution. Okay, you have to make sure the condition is very strong. It has to be all variable independent. So 8.2 is some important statistics, and any function of random variables constituting a random sample is called a statistic. Okay, statistics is kind of like a random variables. Okay, any function of the random variables constituting a random sample is called a statistics. Let's look at some definitions of sample definitions. Okay, so location of measure of sample. We also have sample mean. We select a group of data from the population. We find a mean value. That's called a sample mean. Okay, sample mean value is the same thing as what we learned before about the mean value in the chapter 1. We learned that. Mean value, add all the data together divided by how many data you have. Okay, so add all the sample data together divided by how many data you have. Okay, this is the first definition, the mean value. You can use static crunch to find the mean value the same. And then the sample median. So the median you have, if they have odd numbers, is xn plus 1 divided by 2. And if n is odd, we learned this one before, and xn over 2 plus xn over 2 plus 1, and 1/2 the middle 2 divided by 2 if it's even. If even, okay. For example, 1, 2, 3, 4, 5, and then the median of this one is 3. And if 1, 2, 3, 4, the median is going to be add 2 and 3 together and then divide by 2. Okay, so we have the same definition as what we learned in the chapter 1. The sample is just a data. It's just a small group of data. It's just a group of data, a sample data, but all the method will be the same. Okay, for the sample mean value and the sample median will be the same. Example 8.1 is pretty simple. You can look at that yourself. Okay, variability measure of sample. Also, we have sample variance. Population variance, we use sigma. Sigma square is the standard population variance. Population standard deviation, we use sigma. Okay, but the sample variance, we use S square is a sample variance. Okay, is 1 over n minus 1 xi minus x bar square, I equals 1 to m. Okay, but for the population variance, the n minus 1 is m. If you check the previous one, you can see that. And then the variance of the sample is defined this. And also, you look at this. The computed value of s squared is given sample is denoted by s squared, which is sample variance. Note that s squared is essentially defined to be the average of the square of the derivative, also over deviations of the observation from their mean. The reason for using n minus 1 as a divisor rather than more obvious choice of m is we're going to introduce that in chapter 9. If I use 1 over m, if I do 1 over n, is if I use 1 over n, then is a bias estimate. Okay, if you use n minus 1 in the chapter 9, we're going to explain why we use n minus 1. If we use n minus 1, it's going to be unbiased estimate of the variance of the population. Okay, so 8.2 it explained how you do the mean value. Mean value is sample mean value, add all the data together, 12 plus 15 plus 17 plus 20 divided by 4 is the mean value. And the sample variance, you find the mean value, subtract, use each value, subtract the mean value, plus add all of them together, divided by 4. You have four numbers. The sample size is 4, so subtract 1 is divided by 3, and you find the sample variance. Okay, and in the video when I do the homework, I will also introduce how to use the software to find the sample mean and the sample variance, like a StatCrunch or Excel. You can do both. You can use either one of the software to find the sample mean and the sample variance. Okay. All right. So the next is theorem 8.1 is the S square. Basically, you basically what it does is you FOIL the you FOIL the completed square, minus 1, I equals 1 to n xi minus x bar square. So you FOIL this one, you're going to have 1 over n minus 1 and add all the xi square minus 2x bar xi and plus x bar square. Well, this one, you know that you add all the x bar together give you let me check. Okay, so if you add that together, it's this one, and you can simplify that as a minus 1. I equals 1 to n xi square. Okay, and you can minus 2x bar. The x bar can take it out because it's mean value of I equals 1 to n xi and minus n x bar square. Okay, so that's you prove that by definition. Now the sample standard deviation, and if you subtracted that, okay, so then you got the whole thing. The end is you add all of this. Let me check. Okay, this is x. Tell me say. Okay, this x add together is going to be n times x bar again. So the whole thing will be n minus 1 I square minus n x bar square, or you can just do okay, so you can also change the x bar into 1 over n. 1 over n and cancel out is 1 equals n to n, and then xi square. Wait, xi x square. Okay, so it was n x bar square, but x bar, you can change the x bar 1 over n minus 1 I equals 1 to n xi square minus the x bar, you can change into xi over n square. That makes sense, right? X bar, you can change that, and then the n can cancel, but I still have an n remained, so 1 over n minus 1 and I equals n to n xi square minus the n cancel 1, that out, this was m xi square. Okay, and I from 1 to n. So now you can factor the n out. You can take a 1 n out is n 1 over n times n minus 1. But if you multiply the n as a denominator, you have to multiply the n on the first term, I equals n to n xi square. Okay, and the 1 over n is factored out, is xi I from 1 to n square. So this is another definition, but it's the same as the original definition, but just the simplified. You are going to only have xi. You don't have to find out the x bar anymore. Okay, the mean value anymore. Also, there is another definition about how you find the sample variance. Use this formula. 8.3 is another formula. Use this formula. Another example of using this formula to find the sample variance. Okay. All right. The sample range use the maximum value minus smallest value. We learned that in the first chapter. Okay. So 8.3 is sampling distribution. The probability distribution of statistics is called a sampling distribution. Normally we would like to use, for example, we have too many data in a population. 1 million, for example, if I want to estimate the average of the weight of a bottle, for example, Coke, we want to estimate the mean value of the weight of the Coke. But if the population is 1 million bottle, I don't want to measure this 1 million bottle. It's too much work. So I can probably just randomly choose 1,000 bottles and measure the weight, take the mean value, use this sample mean value or sample variance to estimate the population statistics value. Okay, so use the sample to estimate the population mean. Use the sample mean estimation population mean. Use the sample variance to estimate the population variance. So this one, let's see. The probability distribution of X bar is called the sample distribution of the mean value. So sample distribution mean. Okay. So 8.4 introduce sample distribution of mean and central limit theorem. The first sampling distribution to be considered is that of mean of X bar. We know that X bar is defined as 1 over n x1 plus xm. Okay, and then we know that this one, okay, theorem 7.1 in chapter 7, I think that maybe in the previous one. So the mean value of the sampling distribution is 1 over m mu plus mu. You have n over mu, so it's going to be 1 over n. Oh yeah, we did this one in the previous section, in the previous work. 1 over, you add all the mean, and you have that, you add all the mean together and divide by n is multiplied by n over n mu. So the sample mean is also, the sample mean of a normal distribution is also equals mu, but the variance of the mean value is 1 over n square, and sigma square plus sigma square plus sigma square, and is, because you have n here, so it's n sigma square. And then the standard deviation is going to be square root of n over sigma. Okay, so this is, I probably have to use this, yeah, X bar. Okay, so this mu is population mu, this sigma is population sigma, population standard deviation. So the central limit theorem is, if X bar is the mean of a random sample size n taken from population with mean mu and a finite variance sigma, then the limiting form of a distribution z equals X bar minus mu sigma over square root of m. You, in the previous chapter, after you did the homework part, you'll know that we learned that how to convert a distribution, a normal distribution, into a standard normal distribution. What do we do here before we do x minus mu over sigma? This, if x is a normal distribution, mu and sigma. Okay. Now, if we do use the transformation z equals x minus mu, you got the mean value is 0. And divided by sigma, the standard deviation is 1. We can convert any normal distribution into a standard normal distribution. Okay, this is the same idea, but it's not exactly the same, but it's the same idea. You use X bar, we just proved that X bar, the mean value of the sample is mu, and we also proved that the standard deviation of the variance is sigma over square root of m. So we use the same formula, and X bar minus mu, this gives you a mean value of 0. Divided by sigma over square root of n will give you the standard deviation 1. So if n goes to infinity, which means it's a big, large sample. Well, a large sample, if you have a normal distribution, okay, large sample, then it goes to, as long as n is large enough, it will be a normal distribution. Okay, close to the normal distribution. Then the standard normal this one are based to standard normal distribution of 0, 1, which is, you can also do a normal distribution of 0, 1 is a standard normal distribution. Okay. So the population approximation of X bar will generally be good if n is bigger than equal to 30. What's the meaning of that? It means Like if you have a big sample size, okay, if you have a big sample size, okay, then if it's n bigger than equal to 30, you can use the normal distribution to approximate it. For example, there is a picture here, okay, and you have a picture here. N is large, is near a normal distribution. N is small, is not N small to moderate. N is close to it, but if it's N large, you have a near normal distribution. Okay, the normal approximation for X bar will generally be good if N is bigger than or equal to 30, provided the population distribution is not terribly skewed. So the population distribution, well, if it's normal, for sure the sample is normal distribution. But as long as the population distribution is not terribly skewed to left or right, okay, so if n is bigger than or equal to 30, the sampling distribution is also a normal distribution. If n is less than 30, the approximation is good only if the population is not too difficult to form a normal distribution. Okay, if the population is already a population very good normal distribution, then even the sample size is small, the sample is also a normal distribution. Okay, but if the population distribution is not really skewed left to right or not really bad compared with the normal distribution, you still have a little bit bell shape, then even you have large sample, you still can use normal distribution to approximate it. Okay, let's look at an example. Example 8.4. An electrical firm manufactures light bulbs that have a length of life that are approximately normal distributed. Okay, so the population already is a normal distribution. With a mean equals 800 hours, a standard deviation equals 40 hours. Find the probability that a random sample of 16 bulbs, you see the random sample, okay, so now we're using sampling distribution, the random sample. The random sample of 16 bulbs. So we have a population, though we just choose a sample. We choose a small sample from the population. We check this sample, we just do the research on this sampling, this 16 bulbs. Well, the probability of these 16 bulbs will have average life of less than 775 hours. Okay. So first, the population itself is a normal distribution. 840, okay, X population itself is a normal distribution, 840. Now, my question is, what is the distribution of the sample of this sample? Okay, this sample also a base normal distribution. It also have a mean value of 800, but the standard deviation of this sample is 40 over square root of 16. Okay, square root of n. So this sample is a normal distribution, has mean value equals 800, has a standard deviation which is which is 40 over square root of 16 is 10. So now it is still not a standard normal distribution. So if we want to use the standard normal distribution to find the probability, we still have to convert this into standard normal distribution. So Px is bigger than, less than 775 hours. We still have to convert that x into a z-score. So x minus mu over sigma over square root of n. Because this sample, the sigma is sigma over square root of n is not sigma. Okay, it's a sample standard deviation. So less than 775. I just find that 800 is mean value. I find the sigma standard deviation sigma over square root of n, which is 10. And then this is a z-score. Okay, standard normal distribution. Now z is less than. You find that this one is negative 2.5, and you can directly use the normal distribution table. In the previous chapter, we introduced that. This gives you 0.0062. Okay, so the difference between this chapter, this section 4, from the previous one is previous one when you find the population, z-score is x minus mu over sigma. Now, when we find the z-score is x minus mu, still have the mu is normal distribution, but if it's for sample, now we're doing sampling distribution. So it's sigma over square root of n. We're using this formula to find the z-score, then continue finding the probability. Okay. So the next one is the next example 8.1 is the same idea. We use this z-score, this formula, to find the z-score and find the probability. Okay. So next one is sampling distribution of difference between two means. Okay. Basically, we have you have two. If the independent sample size of n1 and n2 are joined randomly from two populations, so now I have two populations. We select two samples. So the first sample we have n1 sample size. Second sample we have sample size n2. Okay, and now the mean value of the sample is the difference between these two is x1 minus x2, which is mu1 minus mu2. That's not a big problem. The difference of these two, okay, this a difference mean of these two sample, and then the standard deviation, or when we say the approximate normal distribution with the mean and the variance of the difference is n1 sigma 1 square plus n2 sigma 2 square. If you remember in the previous section when we do the ax plus b of the variance in the previous one, if you have y equals ax plus b, the sigma square of the y equals a square sigma square. Okay, if you remember that. And if you have the previous one, x goes to x has the variance of x is x square. Okay, in the previous chapter, if you have that plus b, okay, I probably have another b, x1 plus b x2, and then sigma y square is x1 square plus b square sigma x2 square. Okay, in the previous section you learned that if you have a linear combination of x and y and x2, the mean value is just a mu plus ax mean value plus b times mean value of b of x2. But standard deviation you have a square. You have a square of the both coefficient. And if they're independent, this is if they're independent. If they're not independent, you still have 2ab covariance of x and y, well x1, x2, if you remember that. Okay. If they're independent, this one is 0. If they're not independent, you have to add the 2ab covariance. Okay. This is the previous section we learned that. So you have x1 minus x2 if they're independent. So you have this, you just multiply, add the n1 sigma 1 square plus n2 sigma 2 square, because you look at the coefficient. Now if you define y equals x1 bar minus x2 bar, now look at the coefficient sigma 1 square. Okay, the coefficient of 1 is 1, so square of this 1, so sigma 1 square plus sigma x2 square. Since they are independent, since these two x1 x2 are independent, okay, you don't have covariance. So sigma x1 square is we learned that sigma x1 bar equals sigma 1 over square root of n. So it's a square, you square this, so it's sigma 1 square over n1. The other one, since the negative is the coefficient negative 1 square is positive 1, so it's going to be n2 square. Sigma x2 bar equals sigma 2 over square root of n. You square this, you get n2 sigma 2 square. So that's why you have sigma x1 bar minus x2 bar square equals sigma 1 square over n1 plus sigma 2 square over n2. That's why you have this. Okay. And also, once we have the mu value, once we have the mu, we have mean value, we have the variance. Then what we can do, we can we have the we can use the z. Z is for the z-score. We use that x1 minus x2 bar, okay, minus mu1 minus mu2 over square root of sigma 1 square over n1 plus sigma 2 square over n2. Well, this is it's eventually it's still from the same idea, x minus mu over sigma over square root of n. It's the same idea as here, okay, but just now the sigma is the combination of these two, take a square root, okay. So it's still the same idea. Sorry, it's x minus mu over sigma. So now the sigma is square root of the combination of these two. So it's the same idea as this z-score formula, okay. So now we have the z-score, and use this one to once we give x1, x2, we can use this formula to find the z-score. Okay, use this formula to find the z-score, and you do the example. The case study 8.2 is pretty simple. Is application of the z-score, and you can look at how you apply this formula to find the z-score. First, you find mu1 minus mu2 give you mu equals 0. Instead, a and b part they have the same mean value. And then n1 equals n2 equals 18. Find out the standard deviation of sigma, and then use this formula to find the z-score and find the probability. Okay, so example 8.2 is the same idea. Everything is given. Mu1 is given, mu1, mu2 is given, sigma 1 is given, sigma 2 is given, and mu1 is given, mu2 is given, okay, which means the x bar, and the x bar is an x bar mu1 is, all of them is given. Then you can use that to find the standard distribution, okay. So mu of x1 minus x2 is 0.05, subtract mu1 and mu2, okay. So basically everything is given, and n1 is given, n2 is given, for example 8.6. We just need to apply this formula to find the z-score, okay, and ask and see what it asks for. It asks you for the difference of two. Sampling is px1 minus x2 is a normal distribution. Find the z-score and apply it. It's pretty straightforward. You can read that. Okay, so I think this is this week you just have to read the first 4 lessons. If you have any questions, just feel free to email me. In the next video, I'm going to look at more homework problems, see if you have questions, and how to apply the sampling distribution to solve the real problems. Okay. Then I also introduce how to use the StatCrunch to find all the mean value and the standard deviation stuff. Okay, again, if you have questions, just feel free to email me, okay? Read the textbook, spend 2 or 3 hours, read the textbook again, and read those examples, see if you understand it, and then do some homework practice, okay?